Hi, here we'll look at the schematic diagram of the 68 KB board. As you can see, here is the sort of like full diagram. It's from DipTrace PCB software, and I basically don't use any wire connections between the integrated circuits. As you can see, all you can see is the pinouts with their labeling on the side. So let's have a look at, say, the CPU, the main chip on the board. I'll just zoom in a little bit. Okay, here's the CPU. As you can see, it's got bunch of address lines up to A23. There is no A0, so it's basically addressing even bytes of memory up to A24. Then you got the CPU clock that comes from the external clock, depending on what sort of CPU you're using. Some of them are 8 MHz, some are 10, and so on. These connections are not being used in the design. And then you've got a number of other lines here, like valid memory address and enable and so on and so forth. Some of the other important pins are like reset and halt. They're usually driven by the reset circuit, which is part of the DS1233 IC, which basically gives like hundreds of milliseconds delay on the startup, and usually the reset and the halt lines are connected together. So you'll see on the board a set of 4 terminal pins marked H, R, A and V, and basically you connect the reset and halt lines together and AS and VPA lines together. Obviously the other pins, as you can see, are the ground and +5. Then you've got a set of 16 data lines. They're connected to either the memory chips or some of the communication or peripheral chips, and the memory chips are low address and high address. So here's the low address RAM or NV RAM chip, and here's the high data RAM chip. Read-write line is also very important, and usually, as you can see on the memory chips, you got separate write and read lines. So they're decoded from this R/-W with the GAL chips that I'll explain a little bit later. And these are basically the interrupt lines going to the CPU. Now some of these other lines, as you can see on here, are pulled up high, so they're not sort of being used during the use of the CPU in this design. Now some of the other ICs, as you can see on here, are the 74S164, and basically this is a divider. It can divide by 4 or 8, and that's to do with the dividing the clock or counting the clock cycles together with the GAL chips to enable the ROM part of the memory to be shifted from low RAM address to the high RAM address, because some of the ROMs that are used within the 68,000 designs sit in the high RAM area, but the vectors or the reset vectors for the 68,000 CPU are in the low end of the memory space. So that's the reason for the 74LS164 on the board. Then you got the 74148, and that's to do with the interrupts, and usually, like in this case, it's just interrupt from the one of the comms chips, and it goes to interrupt 3, and then it gets decoded and put into the CPU. Here's the clock for the CPU, and this clock is being used for the comms 68681 chip. In this case it's 3.6 megahertz. Now let's look at the memory chips. This is NVRAM. This is a high data RAM. As you can see, it goes from D8 to D15. It's got all the address lines that are being used, and then you got separate write and read lines, and you can see it's the upper write and upper read, and these signals come from the GAL chips that are decoded from all the other signals coming from the CPU. Now the last one here is marked ROM. So basically what's done in this design is use half of the NVRAMs as ROM and the other half as RAM. And the reason for that is just to save half of the RAM area of the memory chips and not being overwritten during use of the board. Okay, so we'll go on, and the next thing to look at, oh yeah, there is also the chip select lines, and they also come from the GAL chips. This is one of the GAL chips, as you can see, and that basically takes most of the high-end address lines, the read-write and the address stable line, and then provides all the chip selects for the serial input output, the RAM, data acknowledge, the ROM side of things, and this, again, the serial chip 68B50. And here's some of the other data lines. So it's not fully decoded, but it's well enough for this design. Now what is missing on here is this line LDS, which should be connected to pin 18. So in the modification there is a connection from pin 3 to pin 18 of the GAL chip. Now if we look at the comms or UARTs, in one of the designs you can use the 68681, and it's got 2 serial ports on it together with input port and output port, and it's using the low-end data address lines for its communication, and needs that 3.6 megahertz signal, and it needs the 4 address lines to be able to look at all the registers that it needs. And there's also all these other control lines that connect to it, like the reset, the chip select, the read write, and so on. Okay, that's about enough for that one. Now, if in some of the designs you might be able to use the 68B50. This is the higher frequency version of the 6850 chip, and again it's connected to the CPU by the low-end data lines, so you need the LDS line to go into it. You need the chip select, the read write, the enable. You only need 1 address line to address the registers, because there's only like 3 or 4 registers you can address on this IC. This is the received data line. The clock is 1.8 megahertz, and all these other lines are tied low, and you can have the reset ready to send, and I think clear or data clear is connected to 0, and interrupt is not being used. Now this 1.8 megahertz is not on the board, but you can probably divide or get that signal from the GAL2 chip, because there is a 3.8 megahertz clock going into pin 1, and with these 4 pins here that are spare, you should be able to divide by 2 that signal and provide it on one of these pins, and then connected back to pins 3 and 4 of the 68B50. Now GAL2, as you can see, is just used to decode the upper and lower read and write lines and provide this divide by 2 clock signal. And that's basically the function of that one. So you've got plenty of other spare pins if you want to add some functionality of decoding or control of the board using this GAL chip. And like I said, this GAL one I mentioned before is just basically address decoding for all the chip selects on the board. And now looking at some of the terminal connections, I already mentioned this one here. The divide by 4 and divide by 8 are provided via this terminal block or connector, and it gives our MEM signal that goes to GAL1 chip, and that's that memory enable disable to be low end or high end of the memory while you're addressing the RAM or ROM of the memory space. So it's being used in GAL1 chip. The other connections that you can see are the terminal block where you get all the power into the board, and also the reset comes in there. This is the reset button on the board. This is basically the output port of the 68681 there, and it's got 8 pins as an output, and it provides only like 6 pins as input. And the 2 terminal connections are marked RX and TX term, which is the primary one. This is the secondary or auxiliary one that comes from there. And I think I've marked the one from the 68. Where's that one? There's the 68. Oh yeah, there it is. The terminal B from the 68B50 comes out on these 5 pins here. So that basically covers all the sort of functionality of the or schematic diagram of the 68 kV board.